On to example 1. So we're supposed to determine the mean of the means and the standard deviation of the means from the given parameters of the population and sample size. Now, notice what I called these symbols. Okay, so mu is the population average, right? But mu sub x bar, mu sub, as in subterranean, right? Sub below, x bar. So it's the mean of the means. What does that mean? Okay, so if I go back to when we talk about looking at people coming out in the hallway from room to room to room and telling me their X bars. So I go from one room and find an X bar there, the next room find an X bar there, next room find an X bar there. And I walk all around the building and I get all the X bars. Then I should be able to add up the X bars that I got and divide by how many rooms there were, and I would know the mean of the means, right? So it's the average of those X bars, the mean of the means. Okay, so I need to find the mean of the means, and I need to find the spread of those means. How far apart are the rooms from each other, and what would be the collective average? Okay, so suppose that mu is equal to 100, so the population mean was 100, sigma was 30, and n is equal to 40, and I know nothing about the shape of the original distribution. Okay, well, I know the shape has to be normal, and I know that because the original distribution, even though I know nothing about it, I know that I'm taking a sample of size 40, which is bigger than 30, so that means the distribution is normal, right? It's this factor right here. If I know nothing about that original distribution, right, if it's not normal or I just don't know, then I need n to be larger than 30, which it is, it's 40. So I know it's normal. Now the center, mu sub x bar, should be equal to mu, which in this case was 100. So that's my mu sub x bar. My spread is sigma over the square root of n. That's how far the rooms should be apart from each other, if you want to think of it that way. So you take 30, which was your sigma, 30, and you divide it by the square root of n, which is 40, and that comes to about 4.743. Again, use a calculator or whatever you need to figure that out. Okay, what about if the mean was 100, the sigma was 30, great, but n is only 20, and I know nothing about the shape of the original distribution? Well, then you're in trouble, because if you don't know anything about the original shape, you can't assume it's normal. And if you can't assume it's normal, then you need n to be greater than 30. But we don't have it greater than 30, we only have 20 right here. That's a problem. So we cannot determine the shape because n is equal to 20 is less than 30. And since the original distribution is not known to be normal, I can't do anything, right? I can't tell you the mean, I can't tell you the spread. None of the rest of the central limit theorem stuff was going to hold because n is too small and I don't know the original shape. All right, what about C? Uh-oh. N is 20 again. Look out. Ah, but I know that the original distribution was normal. Well, then that's fine. If I know the original distribution is normal, that's when n is equal to 1. Then it's totally normal when n is equal to 20. Sure. Right? The original distribution is normal, so therefore my distribution will be normal. The distribution of the sample means will be normal. Now, the center of those sample means will be mu sub x bar, which is equal to 100. And the spread will be equal to sigma over the square root of n, which is 30 divided by the square root of 20, which comes to about 6.708. Use a calculator, use whatever. Alrighty. All right, what implications does this have for the central limit theorem? This whole, the spread shrinks, right? If the spread is shrinking, what's that going to mean for our probabilities? Let's look at 800. Now remember, 800 is only one standard deviation away, right? So one standard deviation away, let's look at it when n is equal to 1 and n is equal to 30. And we're going to find both of these. Now, I drew this ahead of time with, well, a program you can see, and I found both of them, but we're going to learn how to find both of them with Excel. You got it. Excel and with StatCrunch. But before we find that, let's see if the pictures make sense, all right? So this purple curve right here, see that? That's when n is equal to 1. It's got a lot of spread, a lot of variability, okay? And then this blue curve right here, this tall skinny one, that's when n is equal to 30, okay? 800 is over here, see it? There's the mean of 1,000. 800 is one standard deviation away. So this area right here is what we're looking for. And then look at the blue curve, right? See how tiny it is? You can't even see it. It's going to be really small. Oh, look, it's 0.000002. All right, so let's go find it. Let's prove to ourselves that this is the case. Whoops. You need to see my background. Okay. I'll make this a little bit larger so you can see. Let's use StatCrunch first, just for the heck of it. So we go to Stat, go to Calculators. We want normal, because we said this was normal. The mean was 1,000. The standard deviation originally is 200. Oops, 200. And then I want 800 right here. Right? I want the probability that x is less than 800 compute. There we go. Got a picture. Take a snapshot. If you watch the Chapter 7 videos, you're well used to this. This is 8.1, example 1. Oops. This isn't really an example, is it? It's kind of its own thing. So, explanation part 1. I'll call it that. All right, export. Cool. All right, now I'm going to do it again, but I'm going to change the standard deviation to 36.5, which is what it is for the second one, right? And look, it's so tiny, it's not even graphing it. Take a snapshot. And then 8.1 explanation. I think I called it 1 and 2, so let's do that. Export. Okay. All right, let me go to, actually, I'm going to bring this down. My results, remember? Oh, I called it part 1. Oh, well. Click on that. Copy. And if this happens for you, I'm going to always trust this particular publisher because I know StatCrunch is trustworthy, but that's up to you. So I'm going to click that little box and say run. So if that happens, all right, then I go here. I'm going to paste that sucker in here. There it is. All right, so you can see that 0.158655 right there. And let me go back and grab the other one. Oops, my results. I should have clicked the arrow. Copy. Go over here and paste. There we go. Okay, so let's make a little note to ourselves. So this is 8.1 notes, page 4. We can say that. Part 1, because we're going to have 2 parts here. Okay, so we can see that the probability that x is less than 800 when n is equal to 1 is equal to, and this is from StatCrunch, so I better label it as such. Oops, there we go. It was equal to 0.15865526. Okay. All right, then the probability that x was less than 100 when n was equal to, what was it, 20, 30? Hold on, I better go back and look. Going back. There we go. So n is equal to 30. And by the way, notice I fudged this a little bit. I pretended that I knew all of a sudden magically that the original distribution was normal. Remember back here, way back, page 1, I said I didn't know, and I don't, but for our purposes, it works well for us to just imagine that it was normal anyway. Besides that, it's easy for me to draw. So here, I'll just do it this way. So suppose we know the distributions are both normal. Okay, just assume that for right now because it'll make our lives a whole lot easier. Actually, I'll say assume. There we go. We're just going to do that for our purposes just to make our lives simpler. Okay, now back I go. This was equal to, now notice, this is scientific notation down here. I don't know if you can see it, but it's because it's really tiny, but there it is. 2.1332252 e negative 8. See that? So that means that it's really, 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 really small. It's 7 zeros because you got to move the decimal 8 places over to the left, which I don't think Excel is going to handle very well, but it would be 0.1234567 2. Like that. See? And it turns it into scientific notation on us anyway, because it can't handle it. So just make a note to yourself, that's really, really small. You can see it up here in the bar, right? At point, blah, blah, blah. But when it writes it, it can't handle all those decimals, so it just, because it only has like a 10-digit length from side to side. So it's just going to tell you it's in scientific notation. Okay, now how would Excel find the same thing? Let's see here. So I'm just going to, for my own benefit here, I want x to be equal to 800. I want n to be equal to 1 or n to be equal to 30. I'll find each of those. And then our mean was, let me think, 1,000. No, you don't have to do it this way. This is just me trying to keep track of what we're doing here. And the standard deviation was 200. And that's true. The standard deviation is 200. The standard error, however, is equal to 200 divided by the square root, SQRT, of 30. There we go. So I guess all in all, I really don't need the n equals 1 thing. I'm going to delete that row. Right? So, okay, so I'm going to find these same things down here. No, you don't need to put them in cells, but I think it'll make our lives simpler. Oops, that was 30 when n was equal to 30. Sorry about that. There we go. Okay, equals. Now we have a function for this. Norm.dist. X was 800, comma. The mean was 1,000, comma. The standard deviation. Okay, for the first one, when n is equal to 1, it's only 200, comma, true. True just means that it's going to add it all up, right? That's how you get this little area total. Hey, it's the same number. See? Right there. Okay, then what about when n is equal to 30? Well, it's the same formula, so I'm just going to copy and paste it here. All right, so don't drag it, because if you do, then you're going to have to change everything. So you need 800, comma, 1,000, but instead of 200, I need the 36.5. And of course, hopefully you all know that you could just type this, equals norm.dist 800, comma, 1,000, comma, 200, comma, true. You could just type it yourself. You don't have to use the cell referencing thing. That was just me trying to organize myself, right? Which is nice, like if you're taking a My Math Lab quiz or a test, it's kind of nice sometimes to help set up your spreadsheet and kind of figure some things out for yourself. That's all. Okay. Now, if you're taking paper and pencil final or the paper and pencil midterm, you wouldn't have to do these problems like this, but I could give you these pictures and ask you questions about them, that kind of thing. Okay. Well, I'll just leave that there. It doesn't hurt anything. Okay. So you can see that these numbers that I got are very different from each other, and that's exactly what I put right here. This is really, really tiny, 0.000002. This one's 0.1587. What does this mean for us? It is much harder for a random group's average to be far from the mean than for an individual, right? In other words, it's going to have a much lower probability for the group's average, right, which is x bar. There we go. Oh, no, not a limit. There we go. It is much harder for that to be far from the center because the x bars are much more packed in tightly. Then being off in these tails is going to be a much lower chance than it is for individuals. And let's remind ourselves that we're talking about being one standard deviation away. 800 is one standard deviation away. That's not very far, right, for the individuals. But once you're talking about groups averages, getting a whole group to have an average that low, that is very hard to do. Much lower probability. Okay. So tail probabilities, which is what I call this, being off in the tail, is going to be lower for group bars, right, x bars, group averages, than it is for individuals. Now what's going to do the centers? Well, we'll talk about that in the next video. See you then.